We're going to let x be a random variable whose probability density function is given by the following right here. We want to write down the moment generating function for x, and this can be found in the book that this is based off of. The moment generating function is going to be the following here, and we can write it as so. So we are going to start off with a. Write down the moment generating function for x. So we have mxt, and it's going to be equal to, I'm using t because we could change the variables or whatever have you, but we could use s's also. So let's stay consistent with this and use x. So mxs is equal to the e, so mean of esx. And it's probably be better if we put it in braces. Let's try to stay more consistent, or like let's let me try to stay more consistent. So esx, like this, and this is going to be equal to the integral. We know that we are starting at 0 because of this right here, and x is just going beyond. We don't have any upper limit, so we're going to go from 0 to infinity. We don't need to worry about anything else because it's 0 everywhere else, so we don't need to worry about that. We can see that we have our f of x, x, and then our esx. So our f of x is going to be an e raised to the negative 2x plus e negative x over 2, and that's just from this up here, right? And then we're going to multiply this by esx, and then we have our dx right here. Here what we can do to not do this by parts is actually factor this in. That would be pretty nice. So what we're going to do is, when we're going from 0 to infinity, factoring this in, we have a e, and then we're going to have an sx in here, right? So we have like sx minus 2x. If we factor out our x, we're going to get s minus 2. And then we can do plus, and then we will have we can factor out the 1/2 here. And then we're just going to go from e, and we can factor out x again, and we'll just have s minus 1. And this is dx. So this is what we currently have, and how we can solve for it. It's pretty simple now. We don't have to do by parts, so that's pretty solid. Going on to the next step, we're just going to do this we'll look at each one individually. When we derive this, we are going to have our e to the x on top, of course, and then we just have our s minus 2 right here, plus 1/2, and then we are going to have multiplied by e to the x on top, and then we have our s minus 1 on bottom, and then this is all to infinity over 0. So now that we've done this, I can see that we can actually go back and make this a little bit simpler for ourselves. If we plug infinity into these, it's going to be huge numbers for both of them, which is not what we want. What we can do instead is factor out a negative. So let's rewrite this from 0 to infinity as e to the negative x. So that's just something to note. Inside of here, we'll have a 2 minus s plus 1/2 e to the negative x. Then we're going to have 1 minus s like this. And so that's going to change. So what we really have is an e negative x. And actually, I think I made a mistake when I was integrating this. When you do something like this, you leave the s minus 2 on the top here as well. So this should be an s minus 2, and this should have had an s minus 1. But remember, we're changing this now a little bit. So we have e negative x, our s minus, not s minus 2, now it's 2 minus s over 2 minus s plus 1/2 times e to the negative x, and then we have our 1 minus s over our s minus 1. Actually, we should change that as well to be 1 minus s. This goes from infinity to 0. So now when we plug it in, we know, well, this is negative, right? So really we would move this down here and this down here. So it's just 1 over all of this. And well, all of this and all of this right here, if it's being raised to this infinity, well, it's basically 1 over a really big number, right? So that makes it a really small number. And since it's a really small number, we can just say that it's effectively non-existent in our problem. We don't need to worry about it. So that with that logic, we are just going to be left with, we don't have any more x's in here, so it's just 1 over 2 minus s. plus 1 over, we'll just bring in the 2 here, and we have our 1 minus s. And this is going to be equal to our mx of s. And so that's how we would get the moment generating function for our x. That's part A. In part B, we want to compute the first and second moments. So basically that's e to the x and ex squared. And what this is essentially doing is we are going to be taking our mx of s, and we're taking the derivative of it, the first derivative of it. So this is going to be equal to the derivative of what we have here. So the derivative of 1 over 2s, I'm just going to rewrite this as 2 minus s raised to negative 1. So we'll have 2, I'll do this off to the side. So 2 minus s raised to the negative 1, take the derivative of this, bring the negative 1 in front, and then going inside of here, we're just going to have negative s, which would just be negative 1. And then we would just have our 2 minus s, it'll be squared on the bottom. And so this is effectively going to be just 1, right? 1 over 2 minus s squared. So we'll have plus 1/2 times, and then we have our 1 minus s here. It's effectively going to be the same thing, so we'll just have 1 over 1 minus s also squared. For our problem here, we're going to use that s is equal to 0. And if that's the case, we are just going to get 1 over 2 squared plus 1/2 times 1 over 1. And so that's going to be 1 over 4 plus 1/2, or 1/2, or 1 over 4 plus 2 over 4. So that's just going to give us a 3 over 4. So this is going to be equal to, and I'll write this whole thing out actually. This is going to be if our e to the x is equal to our mx derived is equal to, of 0 is equal to 3 over 4. So that's the whole thing right there. Let's continue on part B. I'm going to go this way for this next one. We're going to want to take the second derivative now. So with the second derivative, you can derive it, and we are essentially just taking the second derivative of this one. Now doing this, we have our 1 over 2 minus s squared. This is going to give us a 2 over t minus, 2 minus t, and this is cubed. I did the same way I did this one. I'm doing the same way with the other one, so I'll do plus, and then we are going to have a 1 over 1 minus s cubed. When you do it, you'll notice that this 2 and this 2 is going to cancel out. So that should be pretty much it. That's what we should have here. We're going to again plug in that our s is equal to 0. So we are going to get 2 over 8 for this one, plus 1 over 1 really, so that's just going to be 8 over 8, which is just 10 over 8, or we can say 5 over 4. So that means the answer for this one is going to be that our ex squared is equal to our m derivative of 0, and this is equal to 5 over 4. And so that's the answer for this problem. That's how we would go about solving it and looking at A and B for this.